The focus of today's lesson, the Arrhenius equation, how does temperature affect the overall reaction rate? You'll notice that I have my kinetics formula page out, my test-taking tool. We have already spent time in our lesson talking about first order, second order, and zero order rate laws. We're going to turn over our test-taking tool page and examine the equations related to Arrhenius. The Arrhenius equation helps me to calculate how temperature affects the overall rate of a reaction and introduces some new terms to us as well, such as activation energy, the y-intercept frequency factor, and so forth. What I'd like to do is to take on a clean sheet of paper and kind of add on some important notes with you to our Arrhenius equation page. For instance, it might be a good add-on, and again, this is just things I've added on, but I wanted to make it neater for you, so you could certainly take a moment with me and add on the following information to your test-taking tool page in a way that's neat and makes sense for you. As we had studied in our video lessons on the Arrhenius equation, we knew how to calculate the fraction. The fraction has an abbreviation of F. How many molecules have an energy that's at least equal to or greater than an activation energy known as EA? The fraction of molecules can be calculated by taking E. Now remember, E is something called Euler's number. It sits on top of the natural log. The opposite of natural log is that E. E raised to the negative EA over RT. EA stands for activation energy, that energy barrier that separates reactants from products. Activation energy must always be placed into your equation using the joules value. Because we're introducing joules and the metric system, R must be calculated with 8.31 as your constant. And T, the temperature, must be in a Kelvin temperature, the absolute temperature scale. The opposite of natural log raised to the power of negative EA over RT, and maybe a little parenthesis here, help for calculator skills, EA over RT will tell us a number, and that number tells us how many molecules are meeting the criteria to actually make it over that energy barrier called activation energy. We talked at great length together in our video lessons about Arrhenius, the Arrhenius equation, relating K, which is the rate constant. Again, from our previous lessons, the rate constant is also involved in the rate law. A is known as the frequency factor. Times E, which is the opposite of natural log, raised to the negative EA over RT. Looks familiar from up here. I went on further to define and just to reiterate some important notes you took from the video lesson. A is defined as the frequency factor. It's relatively constant even though the temperature varies during the Arrhenius equation. The y-intercept of our straight line is indeed a constant value, or pretty close to being constant. It's related to two things, those two criteria of how well a collision actually occurs. Remember that if we raise kinetic energy, we raise the temperature, the molecules are hitting more frequently, and therefore just by increasing the number of collisions, we increase the probability that those collisions will indeed meet the energy criteria of making it over EA, the barrier known as activation energy, and that they'll actually hit with the correct orientation in space. So A is a number, a frequency factor. How often do the molecules meet those two criteria? Having enough energy to get over the energy hump, called activation energy, and they've hit with a successful orientation. If we're asked to calculate the frequency factor, we use the Arrhenius equation, provided the K constant, which is temperature dependent, equals A times E raised to the EA over RT. We also discussed in our video lessons the Arrhenius equation in terms of graphing and in terms of a non-graphing form. In other words, there's a two-point Arrhenius equation, and there's also a graphing form of the Arrhenius equation. The natural log of rate constant 1 set over rate constant 2 equal EA over R times the difference in Kelvin temperatures, reciprocal T2 over T and minus T1. Couple of ideas here. EA is activation energy. Remind yourself when we're plugging out these values, they must be in joules. R is the gas constant, 8.31, when we're using the metric, and temperatures must be in the Kelvin units for this to work out. So every time we're hitting with Arrhenius, make sure it is indeed Kelvin temperatures. The other point that we talked a great deal about in our video lessons, when we're graphing, the natural log of K's versus the reciprocal of the Kelvin temperatures give us a straight line form of the Arrhenius equation, where the slope of that line is indeed equal to the opposite of EA over R. Remember that activation energy is an energy barrier that separates the products and the reactants. In other words, it's always a positive value. With that all in mind, we have enough prep work. Let's begin reading through our lesson number 4, our assignment sheet. So now that we have our equations kind of handy, let's start to read through. Read with me for number 45. What factors determine whether a collision between two molecules will lead to a chemical reaction? There are two determining factors we just discussed that would increase the likelihood of a collision actually making reactants turn to products. And what I've done is taken the liberty of pre-writing this out, and so I'll share my answer with you. Already handwritten out, so I'll just go ahead and put it down. The two things are the energy of the collisions and the orientation of the molecules will determine whether or not a reaction occurs. So we need to know if the energy meets the criteria of making over the energy barrier, called activation energy, and if the collisions were successful with the right orientation. So not only do they have to hit with enough energy, they have to hit with the correct orientation so that bonds break and new bonds can form. Here's also an additional question. According to this collision model, why does the temperature affect the value of the rate constant? I mean, we might be considered here constant. Why isn't it constant when the temperature varies? And that goes back to our discussion we had at great length together in our video lessons about the kinetic molecular theory. And let me just share my answer. You may choose to copy it directly or put it into your own words, whatever you feel most comfortable with. KMT is just my way of shortening the kinetic molecular theory. And we studied that with gas laws. That tells us molecules are in motion. Molecules move, and if we increase their temperature, higher and higher and higher temperature, we're increasing their kinetic energy. We're increasing the speed or the velocity with which they move. And if they have a greater speed, they have greater kinetic energy, more molecules are going to meet the criteria of getting over the energy barrier, the EA, activation energy. At these higher temperatures, the molecules are just more energetic, so the collisions are more successful, increasing the rate of a reaction. Number 48, when ready. The activation energy for the isomerization of methyl isonitrile, again, hear these great organic names. Activation energy is given as 160 kJs per mole. Calculate the fraction of methyl isonitrile that will have an energy of 160 kJs or greater at 500 Kelvin. Calculate the fraction. From our equation page, do you see a helpful formula? We want to calculate a fraction. My eyes go to this one. If I want to know the fraction of molecules that have an energy equal to or greater, I'm going to use this formula, solving for F. Well, we'll take the opposite of the natural log button, that's the E. raised to the negative EA over RT, but of course it has to be in joules and a Kelvin temperature. Let's take a peek at that setup and hit for a common answer. I'll write in black so you can see better. So F is equal to E raised to the negative EA over RT. There's our formula for solving for the fraction of molecules. So activation energy was given to us as 160 kJs. But remember, when we hit this, it must be in a joule. So negative 160,000 joules of energy, and that's a per mole, set over R, the gas constant 8.31, times our Kelvin temperature, 500 Kelvin units. We'll raise E to this entire answer. E raised to that will get us F, where F is the fraction of molecules. Now hit with me to be sure I'm doing it correctly. I always like calculator buddies. So here we have negative 160,000 divided by parentheses 8.31 times our Kelvin temperature, 500. And I get an answer. I want to take the E raised to that, so see what I've done? Second function natural log of my answer, and I get a value. My value is 1.88 times 10 to the negative 17th. I'll hit it twice just to be sure I've done it correctly. 160,000 is my joules of energy divided by R times T, and I get second function natural log of that answer. Oh, I didn't hit that right. Negative 160,000 divided by R times T. Now I've got the same thing twice. Sometimes I just like to keep checking to verify answers. I got that twice. 1.88 times 10 to the negative 17th. So maybe I'll round 89 times 10 to the negative 17th. No units, it's a number. That's the number of molecules as a fraction that are meeting the criteria of activation energy. Let's calculate that again. But now we're going to change temperatures. Instead of running it at 500, let's calculate the mole fraction at 510 Kelvin units. Same formula, but we've raised the temperature from 500 to 510. So E raised to the negative 160,000 joules per mole, set over R, 8.31, times 510 Kelvin units. Let's hit for common answer, see what we find. Negative 160,000 divided by R, 8.31, times 510 Kelvin units. And we get a value. E raised to that value is a number. And that number I find 4.019. How about I go 4.02 times 10 to the negative 17th. That's the fraction at 510 Kelvin units. More interesting than the number is a ratio comparing how many more molecules are meeting the criteria at a 10-degree change. We raised the kelvins from 500 to 510. By what factor did now we see the overall number of molecules actually achieving that activation energy? So let's compare the ratio. At 510, we saw 4.02 times 10 to the negative 17th. That was the fraction at 510 Kelvin units. 1.89 times 10 to the negative 17th was the fraction at 500 Kelvin units. What is that ratio? Well, I already have that value on my screen, so I'll just divide by 1.89 E negative 17, and we get a number. 2.13. What does that mean to us? Well, an increase of 10 Kelvin units, we warmed it up just by 10 Kelvin units, means that 2.13 times more of our molecules have this energy. They have the energy needed to make it over the barrier called activation energy, the energy hump that separates reactants to products. We made note of this before. Generally speaking, increasing a reaction by just 10 units on our thermometer, either Celsius or Kelvin, will double the overall reaction rate. And we do so because we have more and more and more successful collisions to make it over the activation energy. Let's take a peek further on, number 50. For the elementary process, N2O5 forms NO2 and NO3. The activation energy and the overall change in energy are 154 kilojoules per mole. When I solved this earlier, I left out a piece. Could you please add on some missing information? And 136 kilojoules respectively. So it's telling us activation energy, 154 kJ per mole, and the overall change in energy is 136 kilojoules. I left that out when I typed your homework problems up. We're being asked to sketch the energy profile for this reaction, label the activation energy and the overall change, delta E. So we'll go ahead and begin just by simply sketching, just like an XY coordinate, and we'll place energy here. Energy typically measured in joules or kilojoules, and in this particular point they gave us kJs. As time goes by, reactants turn to products. So let's just suppose I have a field here where we're starting with our reactant, which would be N2O5, and I have a barrier that separates it from the products, NO2 plus NO3. When I draw an energy barrier, I climb a hill. This mountain is what's separating me from the reactant to the product. So right here is my reactant, N2O5, and over here are my products, NO2 plus NO3. We're asked to label the activation energy. And keep in mind, activation energy can be found by taking the difference between the reactants and the maximum energy. So how about if we go E max minus E reactants? And I'm going to label that for us, and I'll change color so we can see that. Here is the amount of energy at the reactants. The top of the energy barrier to the amount of energy contained from the reactants is called the activation energy. And this is given to us as a positive 154 kJs per mole. The other part we're asked to label is the 136 kilojoules, and that's called the delta E, the change of the energy in the overall equation. Now think about that. Delta E is found by taking the energy where the products reside minus where the energy of the reactants reside. And what all that means is when we have been reporting in thermochemical equations the delta E, endo or exothermic, this particular reaction looks to be endo, which makes sense because this is a positive value. So from the beginning point where the reactants lie to where the products lie, this is the change in energy for this equation, and that was a positive 136 kilojoules. This reaction is endothermic. For this equation, the sketch is showing the products are at a higher energy level than the reactants. It absorbed energy. Just to kind of show the flavor of an exothermic, let's reverse the reaction. where now the products become the reactants. So the NO2 and the NO3, flipping it around, go on to form N2O5. We're going to read that equation in the reverse order. So now, what's the activation energy for the reverse reaction? Well, keep in mind, from the reactant to the product gives us the overall energy, but the activation energy is from the maximum here to where the reactants were here. How much is that? Well, it's simply the difference of where we started, 154, which would be this entire value. This would be 154. And this value here was what we found as 136. What is that difference? And we'll have the reverse reaction's activation energy. And that looks to be as 18 kJs when I subtracted that. So if I start here and climb this hill, I have climbed 18 units. Starting at 136 and having to get up to 154 would require 18 kilojoules of energy. So the activation energy here, 18 kJs. And notice overall now, this equation is exothermic, where the reactants are at a higher energy level than the products. Let's flip over and see what the next adventure has for us. Looks like we're given data. Here we have a reaction, CH3COO C2H5 with hydroxide. We see a substitution, CH3COO now is a -1 charge, and we've made methanol, C2H5OH. We've got temperature generated for several different trials, and we've got K constants generated at 7 different trials. I can tell by the K constant that this must be a second order reaction, not that we were asked, but just kind of reviewing those skills. Using this graph, the natural log of K versus 1 over the temperature, to use the graph to find the activation energy, reminding us what this is really saying. We want to generate a graph where we have natural log of K on the Y and the reciprocal of the Kelvin temperature on the X. When we run a linear regression, Y equal mx plus b, the diagnostics there, we can find the slope. Once we know the slope, we can plug it into this formula to solve for the activation energy. So we need to generate some lists. First of all, I know I need the Kelvin temperatures, and then ultimately I need the reciprocal of those Kelvin temperatures. So we'll need Kelvins and we'll need the reciprocals. So into my list 1, and anything is there, just clear it out. I'm going to type in as it is. List 1 is 15, 25, 35, 45. But I'll put my cursor back up on list 1 and I'll say list 1 plus 273. Now I have flipped them into Kelvins. So just to jot that down so we can see what I've done, 15 is really 288 Kelvin, 298 Kelvin, 308 Kelvin, and 318 Kelvin units. But in order to graph, we need the reciprocals. So now I'll put my cursor back up on L2 and go it's list 1. 1 divided by list 1 to turn those into reciprocal values. And this is the values that we find. 0.00347, and I'll jot those here. 0.00347, 0.00336, 0.00325, 0.00314. The reciprocal of the Kelvin temperatures in list 1. List 2, we have K constants given to us. So let's type into list 2 as written the Ks, 0.0521, 0.101, 0.184, 0.332. But I also know that when I plot, I need it to be the natural log of Ks. So make your calculator do that work. Place your cursor up on L2 and just take the natural log of list 2 and it will flip it for you. So I have negative 2.955, negative 2.293, negative 1.693, negative 1.103. We have the two lists we need to graph. So again, just remind ourselves what we're graphing: the natural log of K, the reciprocal of the Kelvin temperatures. We're going to run a diagnostics of a straight line where the slope is negative EA over R. So let's go to work doing that. Stat key, calculate a linear regression, choice 4. I have my list in list 1, comma, list 2. And we get this diagnostic screen. For y equal ax plus b, a is equal to negative 5638.34. That's the slope of our line. That's the piece of information we need to calculate the activation energy. This slope is equal to negative EA, which comes out in joules, over the R constant. So the slope is negative EA over 8.31. I just merely have to take the slope from the diagnostics, multiply it by 8.31, take the opposite of it because activation energy is always positive. So 5638.34 times 8.31, and I get my value for activation energy. It's a large number because it's joules. So it comes out to be 46854.6 joules, or if you prefer, 46.85 kJs. What if we were asked to calculate the activation energy from the two-point Arrhenius equation? So instead of generating lists into the data table, we're able to use our equation page where we're asked to use this particular setup. The natural log of K1 over K2 set equal to EA must be in joules over R times the difference of T2 minus T1 as reciprocals. So let's plug that out. My piece of advice is to always take the trials that are farthest away so you get a true representation of the slope of the line. I don't want to take 2 points that are right onto each other. I'm not getting a nice representation of a true line. So take the farthest points possible. The natural log of K1 over K2 is equal to EA over R times the reciprocal of T2 minus T1. All I've done so far is just copy my equation, the two-point Arrhenius equation. So instead of graphing, we'll plug numbers in. Let's call this trial 1, and this will be trial 2, just kind of the farthest points possible. So the natural log of K1, 0.0521, over K at time 2 here, so 0.332. Farthest points possible, equals, we're trying to solve for EA, 8.31 is our R constant, T2 Kelvin temperature, 1 over 318 minus 1 over 288 Kelvin units. We're going to simplify, pulling out for activation energy, which we know will come out positive. Let me simplify the left side first. The natural log 0.0521 divided by 0.332, and I have negative 1.852. Let's simplify what's in this parentheses. 1 divided by 318 minus 1 divided by 288. And this value is negative 3.276. Alrighty, still looking for EA. So the algebra continues. I'll type in next on my calculator sequence negative 1.852 divided by negative 3.276. And that's my value for what EA over R is. To get rid of 8.31, multiply both sides by 8.31, and we get a number. And I'm off. I'm going to re-hit. You do the same, because here's how I know that I'm wrong. 8 made no sense. I have to come back and find a number close to what I calculated before. So I must have hit something wrong. As usual, I start over. I don't give up. I just start over. 0.0521 divided by 0.332. And I just check my work. That looks correct. Let me try this simplifying again. 1 divided by 318 minus 1 divided by 288. That looks fine. So I want to bring this side over. And I got the same thing twice. What I have a hunch is this number really is times 10 to the negative 4th. That's what I'm missing on my calculator screen. Somebody just help me with that. Thank you. That when I recorded this value, 3.276, I neglected to look at the very end of the screen, times 10 to the negative 4. And of course, that's going to be the decimal difference when I find EA. So, negative 1.852 divided by negative 3.276 times 10 to the negative 4th, there's the corrected value, times 8.31, and presto, thank goodness. Thank you for my calculator, buddy. 46978.4 joules, or if you prefer, 46.98 kilojoules. And the reason I was struggling, the reason I knew I made a mistake, I don't give up, I just keep trying. I should get something so close. I mean, they have to be pretty close. The values are indeed coming from the same line. So the values are indeed close. And if they are not, just as I was discovering, keep trying. You're making a calculator error somewhere along the line, perhaps like I was. We have one more to try together. It's number 56. Number 56 also has us graphing and using the two-point form of Arrhenius. Here we have Kelvin temperatures running at a series of trials and some K constants running. Calculate EA and the frequency factor by graphing techniques. So by graphing techniques, very similar to what we've done up here, we have to generate natural log of K's over the reciprocal of Kelvin temperatures and find the slope, knowing that the slope will give us negative EA over R. So what I'll do is just go back to my stats, clear my list out. Let's type in the temperatures as they appear: 600, 650, 700, 750, and 800. I'll turn them into reciprocals of Kelvin temperatures by taking 1 divided by list 1. We have our values. So the reciprocal of the Kelvin temperatures, 0.00167, 0.00154, 0.00133, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This value 00125, I messed up here. 600, 650, 700, 750, 800. It's got off by a line. We'll do the same for Kelvins. Let's go through here for the rate constant K's, 0.028, 0.22, 1.3, 6, and 23. So you'll notice my lists are correct. I have a matching reciprocal of temperature and its corresponding K constant. But I want that to be in natural logs. So I'm going to take natural log of list 2 and I generate the number. And very clearly I see a matching correspondence Kelvin temperature reciprocal versus the natural log of K constant. So for each one of my trials, I've got that entered in correctly. We want to graph. So graph, calc, choice 4 is your linear regression. Mine are contained in list 1, list 2, And let's run that diagnostics. We find from running the graph that A is equal to negative 16108.45. Remember, that's the slope of our line. The slope is equal to negative EA over R. R is our constant, 8.31. So to find activation energy, I type in the slope times 8.31, and knowing that activation energy will always be positive, it's an energy barrier. So 16108.45 times 8.31, and we get a number. 133,861.2 joules, or if you prefer, 133.86 kilojoules. We're also asked to solve for the frequency factor. Remember from our formula page, the frequency factor, related to the frequency of collisions and the probability that collisions are favorably oriented. That frequency factor indicates how many of these collisions are actually successful. Frequency factor comes from the Arrhenius equation. We take a K constant, just remind ourselves here, a K constant, AE raised to the negative EA over RT. This is what we're trying to solve for. So we have a choice. I mean, it wouldn't matter. The K's are, these frequency factors are indeed relatively constant. You might find a slight variance between any of the trials, but not significant. So let's pick trial 1 for no other reason than it's written first. It's K constant, 0.028. I'm solving for A. E is being raised to the negative EA, has to be in a joule, so negative 133,861.2 joules over R, 8.31 times that Kelvin temperature, 600 K units. We're going to pull out A, the frequency factor. Let's simplify what's going on in these parentheses here first. So negative 133,861.2 divided by the R and the Kelvin temperature. E raised to that answer is this entire thing simplified. 2.19 times 10 to the negative 12th. Now, of course, to pull out A, I have to start on the left side. 0.028 divided by that answer, and I get a value. A is 1.28 times 10 to the 10th power. A little over a billion. 12 billion molecules are meeting the criteria of energy and orientation. So this is a number telling us how many molecules are being successful in their collision orientation and with their energy barrier. Let's compare our calculated from the slope of the line to the EA if we were to use the two-point formula of Arrhenius. Always take the farthest points apart. So the natural log of, let's just call this trial 2, this trial 1. Natural log of, remember our formula, K1 over K2. So the first constant, 0.028 from the first trial, and all the way to the bottom, so I get a nice representation of a true line, 23. That's EA over R times the reciprocal of T2 in a Kelvin minus T1 in a Kelvin. Solve for EA. Let's simplify the left side by taking natural log of 0.028, dividing that out by 23. Did you get what I got? Negative 6.711. Let's now simplify what's in the parentheses here. 1 divided by 800 minus 1 divided by 600. We get a value. Is your screen matching mine? Let's take the left side, which we hit was negative 6.711, divided by that previous answer, times 8.31. And we get a value, 133,844 joules, or if you prefer, 133.8 kilojoules. Look how remarkably close we came from the slope of our line calculation, generating with lists, and the activation energy using the two-point Arrhenius equation. And this will always hold true as long as you take the points that are farthest apart from the data table, and you will indeed be calculating the slope of the line. At this point, I'd like you to take out your practice tests, both the A and the B, and begin working on the Arrhenius equation objective. It's objective number 3 found in both of your tests.